Good morning, everyone. Before I start my talk, I would like to express my sincere thanks to the conference committee and the head engineering, since it's like such a long journey from Hong Kong to Brno. And for the conference, I meet new friends and know the people who I talked for a couple of years ago and online, and now I think it's all worth for the long journey. So now I would like to share some of my research about the cellular automaton model for evacuation and resilience in tunnel fire. So it starts from the huge, heavily construction of tunnels. For tunnels in urban area, it could connect different regions. It could deliver goods and transport occupants. So it solved traffic congestions to a large extent. One core of tunnel designing is to ensure that people could evacuate from the tunnel safely when there is a fire or other emergencies. So why tunnel fires would pose such huge threat to people? Because once there is a fire, it will pose a high temperature, those thermal radiation, and it will cause carbon monoxide, and all those will pose a threat to people's life. Oops. And so I just received a question from a manuscript I'm revising on. The expert says why tunnel evacuation or tunnel fire evacuation is so different from other structures, since long corridors, they share similar structures to the tunnels. Here are some of my points. The first is the enclosed structures with poor ventilation, though we have set up some longitudinal ventilation or natural ventilation, but also from the tunnel linings with the heat feedback. So the tunnel fire may be more fierce in an open area. And then it's the unfamiliar environment for people. Though some of us may drive through a channel, we seldom walk through a channel. And since channel is underground, we always have weak GPS signals. We couldn't locate ourselves precisely when we were in a channel and got stuck. And then it's the slow rescue, since when you are in a corridor or in other structures, maybe the fire brigades could get to you since they could drive to the scene. But when there is a fire in the channel, then all the cars are piling on the road channel and they will get stuck. So for those things, we would like to apply some strategies for evacuation in tunnel fires. We have evacuation routes for connect tunnels for both vertical with staircases or some horizontal with evacuation routes. And then we have guiding signages with exit or do not enter signs, or we even add some distance. And then we have more powerful thing smart evacuation systems. However, how could we apply those strategies precisely and accurately? There are two mainstream evacuation approaches, prescriptive codes and performance-based design. Since we are talking prescriptive codes provide engineer a feasible or a flexible way, a direct way to design tunnels. But now we have some extra long tunnels with over 10 kilometers, and those codes are maybe not suitable for those tunnels. So we have performance-based design, and we have the Bible formula: A set should be larger than the R set. Since the A set is larger than the R set, it's quite clear in a timeline that people should evacuate from the channel until the channel is too horrible for people to move through. But things will get complicated if we combine the timeline with a space for both 2 dimensions or 3 dimensions. Because we know that when there is a fire, the fire's development or the fire dynamics will change people's behavior, and people will run along or try to avoid the fire, and then the timeline or the A set and R set may be different because of the fire development. Therefore, I would like to build a evacuation model to fully or like tried our best to consider the fire influence on people's movement. For the fire part, the CFD models like FDS or Parasim provides us like accurate results about the fire dynamics. And then for the evacuation movement, we would like to have some models which is more flexible and we could write our own rules about the fire's influence on people. Therefore, we choose cellular automaton models. Cellular automaton models is a discrete models which divide the space into several grids along and for the width and the height, it's just like the grid sheet of on our table. And people are like signed with on some grids, and those are vacant places, and they could evacuate towards one cell around them for each time step, and then they could evacuate towards the exit step by step. So now we have like CFD models for the fire side dynamics, and we have cellular automaton model for evacuation behavior. And then we would like to combine them or like to embed them. Here, we would like to firstly calculate the fire dynamics about with the time elapsed and how like those criteria will develop, like temperature or like visibility. And then we will draw their development routine as a formula or as other things, and then people will follow those rules, and then they will move step by step towards the exit. Before the model could run for like some scenarios, we would like to firstly make some assumptions of the model. Suppose like it's a case study, and we have like a channel section with two exits here with 100-meter distance, and there is a fire, and it's the length of the channel, and we will make the model choice with the cellular automaton with the more neighborhood. That means people could evacuate from the 8 cells around them, or maybe they could stay still. And for the model size, we choose like 10 meters and 200 meters, and then we have like each grid for the size of 0.4 meters. And for the moving speed, we choose standard moving speed as 1.35 meters per second. And for the choosing target, we use like maximum likelihood estimations. And then we have some specific moving rules for people to evacuate from the tunnel fire. Like for the goals, they are the axis and they are immovable goals. And for the obstacles, we have fire as the dynamic obstacles by generations, and it could be obtained by the FDS simulations. And for the attractors, we have like attractions and alignment from both the people around them and the axis, and it's also called social influence. And for the repeller things, we consider 3 parts here: for the fire, for the cross, and the nearby agents when they are too close with each other. It's a case study of like a fire in the middle of a channel with like 20 megawatts, and it's the development for temperature and for the visibility. And we curve the development of those temperature and visibility until this area is no more suitable for people to evacuate. With this model I just mentioned, that we could do some of the calculations. We could add our own rules and build a lot of scenarios. For example, I have calculated like with the defectors, percentage defectors, like when people are moving from a channel to the exit, they will have some conflicts when they would like to move to the same cell. So some of them may tend to cooperate. They will give that cell to others, and some will fight for the cell. And then we have like some evacuation results, like with different occupants densities and also with densities without fires. And then we could get some preliminary results, like with the density increases, people's evacuation time will increase. But for the tunnel with high density without fire, the evacuation results were pretty good. That without the fire, people are evacuating more smoothly. And I will go on other cases. And then we could like calculate different exit locations. Like here are 7 exit layouts here, and some are like for the same side and some are the opposite. And we could tell like the exit layouts influence on people's evacuation. And then we could do more things with this model, such as we could calculate the influence of the exit signs. So some exit signs are static, that they could not change when there is a fire, but some, like here, is dynamic. When there is a fire, and the sign here will pose like a red cross to tell people it's not available there. And then we could make more calculation to investigate the influence of that kind of setting. And so that is the model I mentioned and I talked about. And then we would like to think, what could we do more about the model we built? Could we like use this model to evaluate the evacuation strategies, or to evaluate whether a channel is robust or like strong to deal with the tunnel emergency, or also for other buildings? Here we would like to introduce or like to get the help with some concept of resilience. It's like the evacuation resilience to evaluate if the channel could handle those fire emergencies and could help people or provide people more help when there is a fire. So for the y-axis, it's like the normal condition, and then with the emergency. And for the y-axis, is the capacity of the channel. Like we know that in normal condition, the tunnel's capacity is larger than the occupant's need, so that in normal operation, the channel could work and provide people transportation or other things. And then when there is a fire, the tunnel's capacity will decrease, since the burning will cause some harm to the linings or the structures. And then some people will find that there is a fire and they will evacuate from the tunnel. And so when there is less occupants in the tunnel, so the occupants' total need will decline. However, when at one point the tunnel's capacity is no larger than the occupants' need, it means maybe at some point and some places there will be a potential injury. Then how the evacuation resilience work? So at one point, if resilience could work, like we add some water mist systems in the channel, and it would suppress the tunnel's development at a very early stage. And then with some like guiding systems, they could guide people's fast evacuation. So we could know that with the resilience work, the occupant's need is always less than the tunnel capacity. Then it will give us a better or a safer tunnel evacuation scene. And then that's the problem, that since we could know like the evacuation process, and we want to calculate what is a safer channel. How could we calculate or like to evaluate a channel is safe or not? Here I would like to propose something at a very early initial thought. For the x-axis is the time to evacuate for all occupants to evacuate from the channel. And for the y-axis is the successful percentage for all occupants evacuate from the channel. As time goes by, that the percentage of people successfully evacuate from the tunnel will increase, and that is the R set, and here is the A set. And so what is an ideal evacuation scenario? For a fire scenario, it's like an evacuation scenario without fire. So no people will get harmed, only they will spend some time to evacuate from the channel. And then we would like to use it as the ideal evacuation scenario with like a score of 100. And then what if a fire happens? People's evacuation speed will be slower down, and with this curve, it's like the evacuation process with a fire. That could be like calculate the evacuation score of the area with the yellow one divided by the green one. And then we could like have several scenarios for small scale of fire, medium scale of fire, and large scale of fire. And each scenario will have different score which depict their evacuation process. So that is mostly about my evacuation resilience thoughts, but since it's an initial thought, I have some like questions still bothering me. It's like, for each scenario, we have a score for the evacuation resilience, for the evacuation process. Then for a channel or for a building, they will meet different scenarios with like different scales of fires, or like we will have firefighting systems, or like technical installations, or like occupants densities. All those things will contribute to a different scenario, and they will have different score. So how could we combine all those scores into a final score for a channel or for building systems? Then here is still a question mark, and I will do more work in the future about this part. So that is basically the things I would like to share and talk for today. It's a modified cellular automaton model, and we built it to study evacuation in a channel fire and hopes to contribute to more buildings, and it considers the influence of fire on evacuation carefully. And then I talk about like some scenarios and of evacuation performance, and we could calculate the process. And then some like evacuation resilience concept is proposed and discussed. So that is mostly all the things here for today, and I would like to, you could like ask more questions or discussions with me. All those will help my research and the research of like evacuation in tunnel fire field. Thank you.
Great, thank you very much for your talk. Any questions from the audience? Okay.
Thank you for your presentation. I think the big difference in a tunnel is that there's no pedestrians there, because only drivers in evacuation, they will leave their car, right?
I'm sorry, but I don't think I could quite agree with you at this point, since when there is a like, car accident and there is a fire and all the cars will piling on the channel road, and all the drivers and occupants, they have to get out of their vehicles, then they have to evacuate, and some like tragedies of tunnel fire accidents have taught us that maybe several tragedies or several casualties would happen due to they could not evacuate from the channel in time.
Yeah, but the existence of the vehicles will reduce the space people can walk. Have you considered this in your model?
That's a good question about the space. When cars are piling on the road, and it will occupy some space. And for like some modeling cases, we would like to block those spaces or those cells as obstacles, and people have to make a detour around them.
Okay, thank you.
First of all, I would like to say that the concept of a score that you presented at the end of your presentation is really interesting. And I was wondering if you can elaborate about the difference between your model and existing software.
Thank you for your question. It's like we all know that Pathfinder is a powerful and a strong software for evacuation thing, and I talked with Brian last day about the fire influence on evacuation thing, since we couldn't find fully coupled for the fire influence on people's evacuation in existing software. So if we could have some collaboration with those software companies, we would like to maybe write those algorithms of the fire influence on people's movement, and that will contribute to a better or more accurate evacuation modeling. Thank you.
Good point. Other questions? Okay, thank you so much.
Thank you.